I'm going to run through a few examples of integration by parts. Just as a reminder, anytime you're taking an integral of a product, usually you want to check and make sure that one value is not the derivative of the inside function or linked to that. But if you have a product that you can't take the integral of just by reversing the chain rule, integration by parts gives you another option. So the idea is that you've got some function written in the form u times dv, which is basically a function written by something that we're going to view as the derivative of something else. But basically it's just a product of two values, usually with variables. You can rewrite that as u times v minus the integral of v du. And I'm going to show you how that works with this example. So let's say I want to take the integral of x times sine of x dx. That's a product, okay? There's no reverse product rule per se when you're working with integrals, although there are a couple of cases that may work. So the easiest way to do this is to label a u and a dv. And usually you want to try to pick a u that's easy to take a derivative of. X, for example, very easy to take the derivative of. Specifically, it's nice if the derivative simplifies in some way. So I'm going to pick x to be my u. I'm going to pick this to be my derivative value, my dv. So I'm just going to write that as sine of x to simplify things here a little bit. And basically you need to fill in the missing values. So basically we have some function u and its derivative du. We have a function v and its integral dv. And that's what we have here. So I don't know the derivative of this yet, so I want to find the value of du. So the derivative of x is just 1. And meanwhile, over here, I have the derivative. So I want to go backwards. I want to find the antiderivative. Antiderivative of sine of x is negative cosine of x. Okay, if you take, and that is going to be my v value. So if I take the derivative of negative cosine of x, I get sine of x. Okay, now you can substitute all of this in this formula up here and that'll work fine. I like the visuals approach because it helps me remember it a little bit better. The formula says to take u times v. And in this case, that's x times the negative cosine of x. And so I'm going to write that as negative x cosine of x. And then it says to subtract the integral of v du, which are those two values right here. So we're going to subtract those two values. So minus the integral of 1 times the negative cosine of x, technically dx. Now, I have minus and negative here. I'm going to divide out this negative and write this as plus. You really have to watch your signs when you do this because you're subtracting an integral. And to finish this, I'm going to get cosine of x, plus the integral of cosine of x is sine of x. And since this is an indefinite integral, I want to add a c. So that's the basic process of integration by parts. Relatively straightforward, relatively easy. Now, some things you have to watch out for. Just because you see a product does not mean that it's something you want to do using integration by parts. You can make a lot of questions tougher than they need to be. And in fact, this is not usually an AP exam topic in the first place. So something that's nice to know, but you don't have to use it. For example, let's say I had something like x times sine of x squared dx. That is not a product rule. Or I'm sorry, that is not a derivative by integration by parts problem. Why? The derivative of the inside function is 2x. Okay? Remember, a lot of times when you see a product, it actually means you're multiplying by the derivative of an inside function. A lot of times that's the chain rule, and that's really what's happening there. So to visualize this, I tend to move the x over here and think, okay, I need a derivative of an inside function of 2x, so I'm going to balance this by multiplying in a 2. I have to balance that by multiplying by 1/2 on the outside. And so then I can take the antiderivative here. That's going to be negative cosine. Inside function stays x squared. This is the derivative of the inside function. Chain rule is going to be reversed, and that goes away when I take the antiderivative. And then the whole thing was being multiplied by 1/2 out in front, and I can have my plus c. So again, not everything is integration by parts. Don't try to force it. Definitely look for those cases where you have the chain rule, because more often than not on the AP exam, that's what you're going to see. Now, some other possibilities. Let's say I have something like the integral of x cubed ln of x dx. Derivative of an inside function here, neither of these is the other's derivative of an inside function, that kind of thing. So this is probably going to be something that's going to require integration by parts. Again, I set up my u and I set up my dv. Sometimes it matters, sometimes it doesn't. I look at this and I say, well, I could take the derivative of x cubed pretty easily. That would be 3x squared. The problem is at the moment I don't know how to take the integral of ln of x. Okay, and whatever you put in this position is going to be viewed as a derivative. You've got to take the integral of it to get the original v value. So it's got to be something that you know how to integrate. So I'm actually going to flip-flop these two values, and I'm going to put the ln of x here because I know the derivative, that my du value is going to be 1 over x. That's very easy to find. I'm going to put my x cubed over here. I can take the integral, so that's my dv, meaning that my v value is going to be x to the 4th over 4. Remember to divide by that new exponent value, reversing the power rule. And again, you follow the formula here. The formula says take u times v, so that's the product of these two values. I'm going to write that as x to the 4th over 4 minus, remember it's minus the integral of the product going this direction. So notice in this case that's going to be minus negative, and interestingly the x in the denominator here is going to cancel an x in the numerator here, so that's going to be minus x to the 3rd over 4. Again, I can divide out the negative there. Minus negative is going to become a plus, so that will make things slightly easier. And then basically I just have to go through the process here. That's going to be x to the 4th. Wait a second, I lost something here. I'm sorry, at the start, that should have been ln of x times x to the 4th over 4. So I need to have that ln of x in there. Okay, now we've got this. So it's going to be x to the 4th over 4 times the natural log of x plus this integral right here, raise the power by 1, divide by that new exponent. That's going to be x to the 4th over 16 plus c. Okay, so not a horribly tough process. And again, I think this little cross multiplying and then subtracting setup really makes things a lot easier. Okay, let me look at some other examples here. One of the really important things that this allows you to do, up to this point we've not known how to take the integral of the natural log of x. And this is going to allow us a way to take the integral of the natural log of x dx. Now you look at that and you say, now wait a second, integration by parts involves having a product of values. And it does. I'm going to turn this into a product. I'm going to write this as 1 times the natural log of x. And so what I can do here, I have my u, I have my dv. Remember, I don't know how to take the integral of the natural log of x. So I don't want to put it here because I'd have to take the integral of this. I'm going to have to put the natural log of x over here. But that's okay. The derivative of that is 1 over x. That's my du value. I can put my 1 here. The antiderivative, or the integral of that, is going to be x, and I can go through the process. It's going to be the product of these two values, so that's going to be x ln of x minus the integral of the product going this direction. X over x is just equal to 1 dx, and then I can integrate. So that's going to be x ln of x minus the integral of that is x. And so it turns out the integral of the natural log of x is x ln of x minus x. Again, if you're doing an indefinite integral, though, you do want to make sure you put your plus c in there. So nice little trick there to take an integral that previously we did not know how to do. Okay, I want to look at a couple more examples here. I want to take the integral of x squared sine of x. A little bit more complicated. And what I'm going to do here in this example is break this up as u dv, and I'm going to break this up as x squared. I'm going to put my sine of x over here. Derivative of this is going to be 2x. Derivative of, the integral of this is going to be negative cosine of x. So what I have here at this point is the product, negative x squared cosine of x, minus the integral, and then I subtract the integral of the product going this way. That's going to be negative 2x cosine of x dx. Now I run into a problem, and it's a pretty significant problem. You notice that, well, first of all, I have minus and negative, so I'm going to move that negative out there. Minus and negative is the same thing as a plus. That'll simplify a little bit. Big problem here, though. Notice, derivative of the inside function. The derivative of the inside function is 1. I've got this x out here. I can't get rid of that x by reversing the chain rule. So what I have here is a second case where I'm going to have to use integration by parts. So what I'm going to do here is I'm going to rewrite the negative x squared cosine of x plus, and I'm going to replace this integral with my new integration by parts. So I'm going to go back over here. I'm going to do a second integration by parts, and I'm going to do a 2x. I'm going to do a cosine of x. Okay, derivative of 2x is just 2, and that doesn't have a variable with it. That seems like it's going to make things a little bit easier when I take the integral later. The antiderivative of cosine of x is sine of x. Okay, so the process here is to take 2x times the sine of x minus the integral of 2 times sine of x. And again, I need a dx there. And I should be able to simplify this. That's going to be negative x squared cosine of x plus, I'll still use my parentheses here, 2x sine of x minus, okay, 2 sine of x, the integral of sine of x is going to be negative cosine x. So that's going to be minus a negative 2 cosine of x. Minus a negative again becomes a plus. So I'm going to replace that. And now I can simplify. That's going to be negative x squared cosine of x plus 2x sine of x plus 2 cosine of x. And then again, I do need a constant here since that's an indefinite integral. You really need to be careful when you go through here. It's very easy to make sign mistakes because usually you're subtracting this value here. In the example I picked, it went away. But remember, if you did have a negative here, that negative would apply to this term and that negative would apply to that term using the distributive property. So really, really watch your signs. Simplify minus and negative when you can, and that'll really make a big difference. Okay? I do want to show 2 other things that could possibly happen here. You saw in this example that I got a repeat, or not a repeat value. You saw in this example that I had to go through an extra step. Okay, you're going to run into cases where you may have to run into a whole lot of steps. For example, if I had the same thing with an x cubed, you're going to have to do a double, actually really a triple set of integration by parts and substitute, many times. That can get really messy and it can get really bad. I'm not going to go through it that way. There is a second approach called the tabular method, where basically you can list out these different values. And the idea here is that you do u dv. Let's say I was doing x cubed sine of x, and it seemed like I was going to have to do multiple steps of integration by parts. What you can do here, you can break it up the same way. I'm going to do x cubed, I'm going to do sine of x. And I can keep taking my derivatives here until I get to a point that would be a stopping point, which the way this works with the sign, it would be when I get down to a constant. It doesn't have to work that way, but a lot of times it can. So I'm going to do, the derivative of this is 3x squared. The derivative of that is 6x. The derivative of that is 6. The integral going down this way would be negative cosine of x, negative sine of x, and then the cosine of x. And basically you can do the same process, except you multiply down the diagonals multiple times. And then you subtract your integral going this way. What's actually going to happen is, because you have all these repeated subtractions, basically your signs keep changing. So you do need to go in, this is going to be whatever the original sign is. This one is going to be the opposite of whatever the sign is when you take the product. This one is going to be whatever the original sign is when you take the product, and then that one is going to be minus. These signs are always going to alternate here all the way to the bottom. And so you can get this answer pretty easily. This is going to be x, it'll be negative x cubed cosine of x. Okay, now it's going to be minus, but it's going to be minus and negative. So that's going to be plus 3x squared sine of x. Okay, plus 6x cosine of x minus the integral of 6 cosine of x dx. And of course, in this case, I know the integral of negative 6 cosine of x dx, that's going to be minus 6 sine of x. So I'm going to replace that. And then you add your constant and you're done. So that's referred to as the tabular method. I don't plan to assign a whole lot of those, but that is the way that that works. And again, you have to watch it. There's no guarantee that you're going to stop when you get down to the constant step. You may be able to stop sooner if you need a derivative of an inside function with a variable in it or that kind of thing. It just depends on what the situation is. So you have to kind of scout ahead to see where it makes sense to stop and where you're going to be able to take your integral. Okay? Let me look at just a couple of other things. One thing to keep in mind, and I'm not going to go through the whole thing here, but one thing to keep in mind is there's no set rule about which goes on which side. You've got to be able to take derivatives of one, you've got to be able to take integrals of the other. Sometimes either way you pick your values works. Something else you want to be careful about. If I had something like x to the 4th sine of x squared dx, and I was trying to break this up, notice that there's an inside function there of x squared. The derivative of the inside function is 2x, which means if I'm going to take the integral, I need to have an x outside parentheses. So if you were going to split this up, and again, I'm not going to go through the whole thing here, but instead of doing an x to the 4th and a sine of x squared, what I really need here is I need a 2x, basically, to balance this. I need an x outside parentheses, so I can borrow one of these x's. I can do an x sine of x squared, and then meanwhile I've used one of my x's. I'm left with 3 x's here, and I would have an x cubed, and then you can kind of go down through your process. So keep in mind, you can borrow, you can move things around. You don't have to keep it the exact way that it's set up in the original problem, as long as it's something equivalent. All right, final example. This one's going to look a little strange. I'm just going to go ahead and tell you what's going to happen here. I have the integral of e to the x sine of x dx. And what's going to happen here, if you actually go through this whole thing, what you're going to end up finding is that e to the x is its own derivative or its own integral. Sine of x, basically you're going to alternate back and forth between sines and cosines. And so what happens is, every time you subtract your integral at the end, you're going to have an e to the x times either a sine or a cosine of x. And what's going to happen there is it's going to end up giving you something that always results in needing another step of integration by parts. And you think, well, I'm just stuck in this infinite cycle and I'm never going to be able to get out of it. So here's a way that sometimes, if you start to see something cycling and repeating, that you might be able to get around it. Watch this very carefully. This is a little bit interesting. What I'm going to do here is I'm going to write this original function, and I'm going to leave this on this side. And I'm going to break it up as u and dv. I'm going to do an e to the x, and the derivative of that is e to the x. I'm going to do a sine of x. The integral of that is negative cosine of x. Okay, so u times v is negative cosine of x e to the x, minus the integral of negative cosine of x e to the x. dx, okay? Minus negative, same thing as a plus, so I'll move that over there and make a plus. Now, I've got to continue with this. So you see here I have an integral of e to the x cosine of x. Okay, something real interesting is going to happen here. I'm going to do my u and my dv, and I'm going to do an e to the x, and I'm going to do a cosine of x. Well, derivative of e to the x is just e to the x. The integral of cosine of x is sine of x. Okay, so what I'm going to end up getting here is an e to the x sine of x minus the integral of e to the x times sine of x. So I'm going to replace that. I'm going to put a big set of parentheses here and just show you what I'm getting here. That's going to be plus e to the x sine of x minus the integral of e to the x sine of x dx. Okay, and again, I can remove some parentheses here. That's a plus, so that's not going to affect anything there. Plus a negative, that's the same thing as a minus. So I can actually take out my parentheses. Usually you're going to have to do a little bit of extra work. And I want you to take a careful look here. There's a reason I left the original integral in place. Okay, I didn't do that in my other problems. Notice that this is the same thing as this statement over here. Okay, I'm trying to get a statement that says the integral of e to the x sine of x equals, and then something over here. So the point is, I can move this over here and just have two integrals of e to the x sine of x. Now, it looks strange. Hopefully you agree, though, this cancels. If I'm going to add it on the other side, I have to add it over here as well. And basically what's going to end up happening here is I'm left with two integrals of e to the x sine of x equaling this stuff over here. That's going to leave me with two integrals of e to the x sine of x dx equaling this over here. Well, I only want the value of one integral. No big deal. I divide by 2, and this side over here also gets divided by 2, and that equals negative 1/2 cosine of x e to the x plus 1/2 e to the x sine of x plus c, and I have my final value. So it is possible that you can have something that cycles and basically returns to your original value. And if that's the case, then you're going to end up being able to basically find your missing value, and when it cycles, you're going to get a repeat of that value. You add it to the other side, and you can divide by whatever that coefficient is. Now, if I had a coefficient out in front of here, you could have some kind of crazy coefficient over here. You know, you could have 7/4 or something and have to divide by 7/4 on both sides. It's not always real pretty, but it is something that'll work out. So, thought I'd show you that example.